Last month, I blood tested for the 6th time in 2025. And note that this is test number 64 since 2015. So with that in mind, what's my biological age? That's what we'll see here. This is using Dr. Morgan Levine's biological age calculator, PhenoAge. And if you have blood test data and you want to calculate your own biological age using this test, there's a downloadable Excel file in a link from my website in the video's description. No email required. All right, so when entering these 9 biomarkers and chronological age, I get a biological age of 35.4 years, which is 17.2 years younger than the chronological. Now, at this point in the video, many people often ask, how good is this clock? So rather than going over that in every video that I make after every blood test, I made a specific video focusing on how good or not that this clock may be. So if you're interested in that, check it out. But for now, let's focus on where can I improve. So the maximum reduction for biological age relative to chronological age using this test is about 20 years. So granted, 17 years younger is not bad. But if I'm not trying to get better, or if I'm not trying to improve, it's more likely that I'll at best stay the same, maintenance, or get worse. So my goal is continuous improvement. So in terms of where I can improve, the obvious would be glucose. And I've integrated some changes in terms of diet for the next test, and I'll cover that potentially in a future video. But for this video, I'll dig deeper into the MCV, or mean corpuscular volume, as that data has been moving in the wrong direction for a couple of years. But that's coming a bit later. For now, let's highlight these 64 tests over 10 years. So why am I testing so often? And I think this is an important point to mention, and I know I've mentioned this in other videos, so if you've heard me say this previously, apologies. But for those who may be unfamiliar, there are many in the longevity space who are testing, blood testing, once, maybe twice per year. And then that raises the question, is once or twice per year representative of a full year average? One could even make that argument for 4 tests per year. Is every 4 months representative of a full year average? We want to get closest to the truth so that we can track year-to-year change to really try to move the biomarker needle towards youth. And if we're only measuring once per year, I'm not sure that that really measures a rate of aging. So with that in mind, for more context, let's have a look at year-to-year change using this clock, as I have 43 blood tests since 2018, which is what we'll see here for year-to-year change for biological age from 2018 to 2025, as I have 43 tests using Dr. Morgan Levine's biological age clock, PhenoAge. So when I first started tracking in 2018 to 2019, I wasn't measuring hsCRP at every test. It just wasn't on my radar. So I only have 3 blood tests over that 2-year span. And over that 2-year span, average biological age was 34.3 years. And then to my point about measuring more often and gathering enough data to have a true rate of aging and evaluating year-to-year change, I started testing more often. So in 2020 and 2021, 6 tests each in each of those 2 years, 12 tests total, and average biological age in both of those years was exactly 33.9 years. So even though in most cases, 1 or 2 tests per year may not be representative of a full year average, in my case, it actually was pretty close to the truth, quote unquote, 34 years in 2018 to 2019, and then also 34 years in 2020 to 2021. But then I started to increase the testing frequency. Over 7 tests in 2022, I had my best year to date, 32.1 years. 7 tests again in 2023, it got a bit worse, 32.9 year average. And then I increased the testing frequency again, now to 8 tests per year in 2024, with an average biological age using this test of 33.1 years. And then after the first 6 tests in 2025, current average is 33.1 years, exactly where it was in 2025. Note that the 2025 average includes the most recent test, 35.4 years, which is actually my second worst of these 6 tests. Now, it's important to highlight here too, note my first 2 tests in 2025 were actually my best so far this year. So if I just stopped and just only measured those 2 tests and promoted online these great data, it would be somewhat dishonest and misleading, because the real story is I've got variability in my data, and everybody's got variability in their data, but it's very easy to cherry pick and show one's best data. And I think the more honest approach is showing all of one's data and then tracking year-to-year change. So that's what I'm doing. So with that in mind, this is a real pace of aging, looking at year-to-year change with many biomarker tests each year and tracking that over time. And with that in mind, I've resisted an age-related biological age increase using this clock, which is good news because even if all biomarkers stay the same, pheno-age increases by 0.9 years for every year of chronological age, which means that starting in 2018, based on that 0.9 year per year increase, in 2025, I should expect to see a biological age that's closer to 40 and not 33. So this is good news. All right, so this is one way to look at the pace of aging or rate of aging by looking at the biological age clock pheno-age, which includes 9 clinical chemistry biomarkers. But for now, let's focus on another example, including the MCV, as I want to improve that as it's a weak spot. So first, we'll focus on the year-to-year change for MCV, and then second, what can I do to potentially reduce it? But first, let's focus on what exactly is the MCV, because I think to most people, it may seem like just a throwaway biomarker, an irrelevant biomarker, but this couldn't be further from the truth. The mean corpuscular volume equals the volume inside of a red blood cell, which is what we'll see here. So starting off with a red blood cell that has a small volume, that would be a low MCV, and then obviously a bigger volume, that's a medium MCV, and then the biggest red blood cell volume on the cartoon, that would be the highest MCV. Now, if MCV doesn't seem like it's an important metric, remember that red blood cells are the most abundant human cell type by far. And they're approximately equal to 80% of all human cells, including liver, immune, etc. So measuring not just total red blood cells, what's in them, hemoglobin, their volume, MCV, the variability in their volume, which is the RDW, and then we could even take it a step further, the omega-3 index, which is the proportion of the fish oil fatty acids, EPA and DHA, that are in red blood cell membranes. These are 5 important metrics that I find valuable to track. Now granted, if you're familiar with the channel, I'm not tracking the omega-3 index in red blood cells. I'm using phosphatidylcholines, but that's a story for another day. So what's optimal for the MCV? And lower is better. And if you want to see those data, I have a new Patreon tier dedicated specifically to what's optimal for biomarkers, including the MCV, but also 34 other biomarkers, which are covered in more than 2 hours of video content, 52 published references, and these aren't the reference ranges. This is what may be optimal based on how each of these biomarkers changes during aging and their associations with risk of death for all causes. So if you're interested in that, check it out. So let's take a look at MCV versus age over that 10-year period, 2015 to 2025, as I have 59 tests over this period, which is what we'll see here. So on the y-axis, we've got the MCV in femtoliters, FL, plotted against chronological age. And then we'll put up a line in terms of what's optimal for the MCV at approximately 90. So when it comes to the MCV, I don't actually have a range. Around 90, as close to 90 as possible, is my interpretation of the literature in terms of what's optimal based on how it changes during aging and its association with risk of death for all causes. So when I first started tracking in 2015 for the first 5 tests, we can see that it was moving in the wrong direction. But then I was able to flip it and move it in the right direction. But this isn't about just looking at 2 different groups of trends. I want to know the average cumulative exposure over time, which incorporates all of the data. And when doing that, average MCV over those first 24 tests was 90.8 femtoliters, which isn't too far from that 90 femtoliter target, optimal target. Similarly, for the next 35 tests, average MCV is pretty close, 90.9. So if we only look at the average over time, it's decent, pretty good news. Not too far from that 90 optimal that I've established as a target based on the published literature. But this is why looking at one's own data and plotting it is important, because you can see over the past 5 years that trend line is clearly moving in the wrong direction. And that's important because the MCV increases during aging. Now, some of this may be related to aging, but another part of it may be related to diet changes that I've been doing to potentially impact other biomarkers that may be moving MCV in the wrong direction. Which then leads us to how can I potentially reverse the MCV increase and get it back closer to that 90 femtoliter target. So to do that, I've been looking at diet and MCV correlations. And for those who don't know, since 2015, every day I've weighed all of my food, or almost all of my food. More than 99% of all food has been weighed with a food scale. I then enter that data into a diet tracking app, Chronometer, and if you want to use Chronometer, there's a discount link in the video's description. I then pull that data into a spreadsheet. So now I can take the average dietary intake in between blood tests, and then line it up with the latter blood test. In other words, if there's a 50-day period in between blood tests, when I take the average of those 50 days, that now corresponds to the latter blood test. So now every blood test is a corresponding average dietary intake, and this applies to supplements, it applies to the average daily heart rate or steps. You can use this approach for anything. Then I can look at correlations. So for the MCV correlations that we're going to see here, I looked at correlations for 99 macro, micronutrients, and foods versus MCV, with the top portion of the list shown here. And I should mention it's the top portion because you can see even at the bottom of this list, the p-value is 3 times 10 to the negative 5. So the list would be far too big to show on YouTube. So if you want to see the full correlation list for diet versus MCV, that's in the correlations tier on Patreon. And that's not the only biomarker correlations that I have. I do correlations for all these big biomarkers. So all of the red blood cell measures that I mentioned, kidney function, liver, etc. So if you're interested in that, check it out. So in terms of the table that we're looking at, the lowercase r is the correlation coefficient. The p-value is the measure of statistical significance. Now note that generally less than 0.05 is nominally significant. When you have 99 comparisons, 5 of the 100 or 5 of the 99 could be false positives. So one way to account for that is by measuring the false discovery rate. And a rough way to do that is by dividing that p less than 0.05 threshold by the number of tests. So when I do that, all of these on the list would still be significant after correcting for an FDR, but that too is a story for another day. In terms of the N, this is the amount of tests that I have corresponding diet data. Now note that although I mentioned I've been tracking diet since 2015, that was from macro and micronutrients. It wasn't until 2018 that I decided, hey, you know what? Macro and micronutrients is somewhat reductionist. I should be tracking foods. I'm assuming that macro and micronutrients can tell the whole story about foods, but technically I should be tracking food intake too, and that can provide more insight. So I have 59 tests that go back to 2015 for macro and micronutrients, but 45 tests for foods. And then also, it's not a dietary component, but body weight. I also included body weight on this chart. So atop the list, and somewhat surprisingly, are Brazil nuts. And a positive correlation indicates that higher intake of the food is significantly correlated with a higher MCV. And note that I said correlated. I'm not at all suggesting causation. The only way to know is by moving the needle for the different foods and see if the biomarker changes. Conversely, if the correlation is negative, that indicates that higher intake of the food is significantly correlated with a lower MCV. Now, so we can see atop the list are Brazil nuts, and that indicates that I may be eating too many Brazil nuts. But only looking at the correlation doesn't tell me how much or how little Brazil nuts, how few, should I be eating to potentially impact the MCV. So for that, let's take a look at that plot for MCV versus Brazil nuts over this 7-year period and 45 tests, which is what we'll see here. So on the y-axis, we've got the MCV, and this is plotted against the average daily Brazil nut intake that corresponds to each test. And first, we can see the correlation. Again, the correlation coefficient would be 0.72, so that's what that red line indicates. And then most recently, for the latest test, I was averaging about 12 grams of Brazil nuts per day, and you can see that that MCV for that test was relatively high, 93. For the next test, I've cut Brazil nut intake to 5 grams per day. And if this is a real correlation, based on extrapolation of the trend line, I should expect to see an MCV that's closer to about 90 femtoliters. Now, what happens if I cut Brazil nut intake to 5 grams per day? Not if, I've been eating 5 grams per day rather than 12. What happens when I cut it to 5 grams per day and the MCV stays at 93? Well, after recalculating the correlations after blood test number 7, which is scheduled for late October, if that's the case, the correlation will weaken and other stuff will move to the top of the list. So for example, maybe ginger and black pepper, maybe I'm eating too much of that, and I'll make those changes for the next test. And it's this continuous iterative process that I've used for many biomarkers, and that's one reason why many of my biomarkers are closer to youthful than they are to aged. So stay tuned to see if cutting Brazil nut intake will make an impact on MCV for test number 7. But this is just part 1 of the blood test number 6 analysis. In the next test, we'll dig into the full blood test report. What diet, supplements, and prescription meds correspond to this 17-year younger biological age? So stay tuned for that video. If you're interested in more about my attempts to biohack aging, check us out on Patreon, where I offer blood test consults, but also post at least twice per day in 4 other Patreon tiers. We've also got a whole bunch of discount and affiliate links that you can use to test yourself that help support the channel, including ultralabtest.com, which is where I get the majority of my blood testing done, the clearly filtered water filter, which I use every day, at-home metabolomics, I'm now up to 20 tests, oral microbiome composition, NED testing with Ginfinity, epigenetic testing with True Diagnostic, at-home blood testing with SciFox Health, which includes the best epigenetic clock of epigenetic clocks, ConquerAging, green tea, which I drink every day, diet tracking with Chronometer, or if you'd like to support the channel, you can do that with the website Buy Me a Coffee. We've also got merch, including Data is my North Star, Figuring Stuff Out is my drug, and the ConquerAging or Die Trying logo, which I've got on here. So if you're interested in that, link in the video's description. Thanks for watching. I hope that you enjoyed the video. Have a great day.